Welcome back. So in the previous lecture I gave some sort of idea what black carbon and elemental carbon and what are black carbon and elemental carbon, organic carbon and brown carbon, how they are defined. Okay. So I hope that you have a fair idea, and I strongly suggest that you should read these nomenclatures, read papers wherein you will be able to find these differences what they have been using. Okay. So what I am going to do in this lecture, I am going to give that how these species are measured. Okay. Just recall the previous lecture, I discussed that elemental carbon and black carbon, they are almost same, chemically they are same, the composition is same, the only difference is by the method they are measured. So black carbon is usually measured by optical methods, whereas elemental carbon is measured by thermal methods. Still we also find one of the very important thing, that despite these things, we had kind of difference in the ratios when we talked about the BC to EC ratios, which we did in some of the sampling sites. So the ratios were slightly higher, especially during the winter time, and some of the time during summer time black carbon and elemental carbon ratios were almost like similar. So the way it is there, that actually sometimes in the winter time there is probably some more absorbing species that is present, or it could be that something there is some process that is happening in the atmosphere through which the absorption is enhanced. Although we have the same black carbon content, but the absorption is enhanced, and since we are measuring the absorption, we are actually measuring the enhanced absorption, and when we are measuring enhanced absorption, you are getting more black carbon, and therefore the BC to EC ratios were similar. We did the same things, we did this experiment. I think I may have or may not have the slides, so just let me see that if I have. So in that one we found that in the urban areas we did find that there are actually some additional absorbing species, although that time we could not quantify them, and then later the terminology came like brown carbon and Hewlett like substances and mineral dust. So in this lecture what I am going to discuss now is measurement of carbonaceous species. So as I said, there are two ways to measure black carbon and elemental carbon. Now remember, here I am talking about the only black carbon and elemental carbon. Here I am not talking about no organic carbon, or I am not talking about the no BRC. So these measurements I am not talking about, but you will see here that thermo-optical methods does measure organic carbon and elemental carbon. Okay. So if you measure by purely optical methods, you are going to get only black carbon. Okay. But if you use thermo-optical methods, you are going to get organic carbon and elemental carbon both. And the name, as the name suggests here, so this means thermo means thermal. Okay, and thermal means you have to introduce the heating system, and optical means some optical property is used, for example absorption, so is used here, and we will see that how here and then here optical measurements, here also the absorption is measured, but here the absorption measurement and here the absorption measurements are for different purposes. We will come to that. Okay. So generally we use purely optical methods, like we have athelometer, soot absorption photometer, multi-angle absorption photometer. These are the three instruments. Of course the PSAP and MAP, they are not actually directly absorption measurements, but they do infer that the kind of absorption, the process that happens by the absorption. So athelometers, what it does, athelometer is very commonly used. One of the most common methods that we use is athelometer, and because we have this measurement of high athylometer is very simple, and you don't need to it's not a time kind of very consuming. You don't have to do, but of course there is actually when you have done the measurements, you have to do some corrections, but that athylometer algorithms takes care of that one. And what it does, it measures absorption at a given lambda. So the absorption starts measuring say from I think 370 nanometer and it goes unto 120 nanometer. So there are actually 7 wavelength that are measured, okay, and in between just about 770 there is a 880 nanometer at which we are measuring and we are calling black carbon. So now you can imagine the situation that absorption is measured as 7 wavelength. So this is actually 7 wavelength. Now we also have a dual wavelength actually, which actually measures only 2 wavelengths, okay. So you have 2 types of athylometers, or you have a wavelength that is measuring only 1 wavelength, single wavelength. So this is also athylometer is absorbing. So but most of the time when we say absorption measurements, it measures as a given wavelength, and as I said that if you are using the lambda 7 wavelength laser beam, then this means you can get at a 7 wavelength you can get the concentration. Then that becomes a problem, that how do you say that which is actually black carbon. So in that one researchers have established that most of the time 880 nanometer wavelength absorption is the correct measures for the elemental for the black carbon measurements. Other wavelengths are not truly representing the black carbon, okay. So when we say, we generally refer to 880 nanometer. Another very important point here to remember is, because it measures the absorption, so somehow you have to convert this absorption into concentration. So and for this purpose conversion we use actually conversion factor, okay. Now here the problem starts, because you are using a conversion factors, and this conversion factor, which is also called as site specific mass absorption efficiency, or sometimes they use cross section. Again there will be a very big confusion here, so just try to understand this one. I preferred to use mass absorption efficiency because it actually related to the absorption and then efficiency, because somewhere down the line you have actually like what you call per unit gram. So efficiency is there, but the other measurements they use cross section because the unit is probably because the unit is meter square per gram. So the meter square, if you see the unit for measure meter square is some sort of, in chemistry, is actually cross sectional area. So and then per gram. So this is how probably they use mass absorption cross section or mass absorption efficiency. As I said that I prefer to use mass absorption efficiency. You can choose any of them. So this measured absorption is converted into BC mass using a conversion factor, and that I said here that this conversion factor. Now there is a problem. This conversion factor is generally used is actually constant. So if we are measuring at Varanasi, I will use the same conversion factor. If I go to Himalaya, I will be using the same conversion factor. If I go to Bay of Bengal, I will be going to use the same conversion factor. If I am measuring very close to the source, say emission source, I am using the same conversion factor. But if I am measuring the black carbon at a remote location where these aerosols are transported, so thus these aerosols are aged aerosols, then also I am using the same constant conversion factor. Therefore, there is a problem actually, some sort of things that this because the mass absorption efficiency can be different for different type of aerosols or different type of emissions. So if you have emissions from biomass burning then mass absorption efficiency may be different, and we have established this one, that's mass absorption efficiency for biomass burning, then coal dominated area, and then aged aerosols, the mass absorption efficiency is very different. And this is probably one of the reasons this actually atherometer measurements are actually, people ask this question, that if you are using atherometer, the reviewer at least will ask that why did you use the same constant conversion factor. And of course, we do not have much information on this one in India. And I think the very first paper I talked where we established that okay, the mass conversion factors are the site specific conversion factors, or mass absorption efficiency must be used. So we will come to that later. Whereas in the thermo-optical methods, the instrument's name is ECOC analyzer. I am sorry, something is, we wrote on that one. And what it does? So it does combustion at various temperature in an inert and oxidizing medium. So both the medium. So as I said, during the inert medium, oxidized organic carbon will come, and during this period elemental carbon will come. But when we are heating at high temperature, some of the organic carbon may be converted to pyrolyzed carbon. Now this pyrolyzed carbon will, now once it is pyrolyzed, it will give rise to the absorption, and then this means if it is giving rise to the absorption, this will be inaccurately measured here. So this pyrolyzed carbon has to be corrected, this correction has to be done. This is very important in the, so this is one of the drawback of this ECOC analyzer, that you have to correct for pyrolyzed carbon, and of course there is an algorithm in that one. So algorithms does take care of this one. Second issue is that at what point, because we are using as a inert medium and oxidizing medium, so what point we will call it as a split point. So split point means, say this is a point, a split point, before all the measurements that were there is organic carbon, and after all the measurements is elemental carbon. Defining this split point is very important, and if you are unable to define this split point very accurately in thermo-optical methods, you may be actually biased, your results may be biased, and you may get wrong results. And in the method itself, this is very beautifully built. Now this is, and this split point is done by measuring the transmittance at transmittance or absorbance. You can say, you can again convert this transmittance into absorbance. So it measures continuously, like here is measured continuously, black carbon continuously measures the absorption at every 5 seconds. It depends on how frequency you use. Every seconds you can put at every 5 seconds. Here also, as the evolution of this organic and elemental carbon happens in inert as well as in the oxidizing medium, it's keep recording the transmittance. So now you can imagine a situation, or let's discuss. Imagine a situation that initially when you have aerosols, you have both organic and elemental carbon. Now when you are heating this one, actually you are removing most of the organic carbon, and but some of the organic carbon will be pyrolyzed, and that can be used here actually. So what will happen? The initial, if I just say initial transmittance or initial absorbance, AI initial, it will be because of food, this elemental carbon itself, because there is no other things that is absorbing. But when you are doing this one, when the pyrolysis takes place, part of organic carbon is pyrolyzed and it is giving the absorption signal. So this means as the heating process goes on, during the heating in oxidizing atmosphere, you will get more absorbance, or you will get less transmittance. So transmittance will decrease, but absorbance will increase. This is actually happening. But there is another problem, transmittance, because you have removed the organic carbon. Transmittance is because of the organic carbon plus black elemental carbon both, but during the when you are doing this one heating, organic carbon is selectively removed. So, organic carbon is removed, this means transmittance will keep on decreasing. So, we will see that we do not confuse, we will see this one how the absorbance and transmittance changes. So, and at the same time, so we measure this in combustion at various temperature in inert and oxidizing medium, means here you do not have, you have 100% helium, and here we usually use 2% or 5% oxygen. Okay. And then simultaneously we measure transmittance through the filter also we measure the transmittance. And this, once it is done, this measures attenuation. So, this means what, that is what I said. So, when it is doing this transmittance or attenuation, there is a different terminology, we will discuss this one. This is sort of absorbance only. The attenuation is measured at 678 nanometer. One problem here is that you should discuss, you should remember this, that here black carbon ethylometer uses black carbon measurements at 880 nanometer, whereas here we have actually signal laser transmittance that is measured at 678 nanometer. I really do not know why both the measurements should have been done either at 880 nanometer or the other one should have been done at 678 nanometer, or we have actually just above 880 we have 670 nanometer. So, we can use that one, actually we can use to compare that. So, but sometimes if you are using a single wavelength ethylometer, you are only measuring at 880 nanometer. So, because if you are measuring the absorptions at different wavelength, and since you know that absorbance can be different at different wavelength, these measurements can give it faulty results or different results. So, in thermo-optical methods, it does not only start combustion at various temperature in inert and oxidizing medium, it also simultaneously measures transmittance through the filter, and this transmittance is converted to the attenuation or absorption at 678 nanometer. So, in principle what it does actually, EC-OC analyzer gives you 3 parameters. It gives EC concentration, it gives OC concentration, and it gives attenuation or absorbance. I think I will take a different lecture on this one, absorbance and Beer-Lambert's law, because this concept is very important, and many a times this concept of Beer-Lambert's law is used here. So, I will take probably, let me see if I can do it in the next class. So, it measures, the advantage of it this thermo-optical method is that is measured, it measures 3 parameters, EC and OC concentration as well as attenuation. So, 3 parameters you are saying. Now, as I remember, and therefore, this can be used, this directly simple method, this EC-OC analyzer can be used to calculate the constant, whether the mass absorption efficiency is constant or not, because we will see that how the definition is there. Okay, let us go in the next slide. So, it actually simultaneously measures attenuation and EC concentration, and therefore, it can be used to calculate the mass absorption efficiency, absorption coefficient or absorption and mass absorption efficiency. So, mass absorption efficiency is generally defined at absorption coefficient divided by EC concentration. And remember, absorption coefficient unit is actually million meter inverse, whereas this unit is given as microgram per cubic meter. So, this means you can calculate microgram, you can calculate in gram, and then meter cube is here, it will go on the top. So, this will become meter cube, and 1 meter minus is there. So, it will be having actually like m2, and then you have convert the mass into gram. So, this is actually very important, and that is how the mass absorption efficiency is there. So, what you need actually? In order to calculate mass absorption efficiency, you need 2 parameters. One is actually absorption measurement and another one is EC concentration. So, if you are measuring in one single instrument, you can directly derive this one, okay. Or the other way is that you measure this by another methods, and then you measure absorption coefficient, you measure by one method, and you measure EC concentration by another method, and this is what is done. Because the problem is that EC measurements is actually mostly done by thermal methods. So, anyway you have to come to the thermo-optical methods. This absorption coefficient measurement can be done by ethylometer, like ethylometer, like I just get. So, this ethylometer, what it does? It actually, so there are two parameters in ethylometer. Ethylometer actually measures this concentration and uses this constant, this mass absorption efficiency, which is constant, which is assumed constant, and then you have this parameter is measured in the ethylometer. This you have inbuilt there, that what is the mass absorption efficiency you have to use at 880 nanometer. This is actually 16.6 meter square per gram at 880 nanometer. So, in principle you have measured this one, you have already data about this one. So, you can calculate EC or equivalent VC. This is one way of measuring the black carbon by ethylometer. If you are measuring the EC-OC analyzer, the benefit is that you can measure three parameters: EC, OC and mass absorption efficiency. Automatically you can derive, and of course apart from the mass absorption efficiency, you can measure the absorption coefficient. Yeah. So, in the measurement techniques of EC-OC analyzer, again let me be very specific here. This EC-OC analysis means actually we are using thermo-optical method. So, this means we have to do thermal and then we are optically measuring the absorption R. So, in the first step what it will do? It will heat, you have samples there, aerosol samples, you have filters on which the aerosol samples are deposited. You take a small piece of this filter and put in the instruments, okay, and you ramp, you start heating, and ramp wise heating is there. So, this means that you for certain period 30 seconds you have fixed temperature, there will be increase in the temperature, then it will be constant for some time, then again it will be increasing. So, and it goes up to 850 degrees centigrades. So, 850 degrees centigrade is assumed that most of the time this carbon will be evaporated, and what we are doing here, helium purging, this is very important. So, helium is actually used here and this is actually inert gas, okay, and this is of course used as a carrier, because when you have this heating will do all the during the heating this carbon will be converted to CO2, and this CO2 has to sent to the detector. So, this CO2 is sent to the detector by helium as a carrier gas, okay, and then it goes to the detector, which we use usually FID, flame ionization detector. So, you are measuring there. One problem that you can imagine here, that when you are heating at 850 degrees centigrades, we know that in this one there is actually carbonate carbon that is there already in the aerosols, and Indian aerosols, which is called CC, and because this carbonate carbon is associated with mineral dust, okay, this dust. So, when you are measuring this carbonate carbon, which is actually, say let us example CaCO3, when you are heating this one, it will also give rise to CO2 plus calcium oxide. This CO2 will be there. Now, here also during the heating process you are also getting C2 from the actual sample because of the organic carbon, and you are getting additional CO2 from the carbonate carbon. So, in principle what will, if you are measuring the FID will not distinguish whether it is actually organic the CO2 from the organic carbon or CO2 from the mineral dust. Then what you do? This, so this will be getting a kind of overestimation. So, in order to overcome this one, what is principally used here, because calcium carbonate is basic in nature, we used HCl vapors, okay, acid vapors. So, when you have HCl, what it will do? This will actually remove calcium carbonate and CO2 will go away. So, whatever the samples, this is called actually acidification, acidified samples. Okay. So, during this, okay, so let me complete this one. So, when you are measuring this one, you do two things. One, you measure with the samples, unacidified samples, and one is actually acidified samples and one is unacidified samples. When you are doing acidified samples, this CO2 from the carbonate carbon will go away. You do not have carbon dioxide that is coming from the mineral dust. So, you only have in the acidified samples, this CO2 will be only remaining because of the organic carbon and elemental carbon. And then because when you are doing, so you can take a difference and you can calculate that how much actually carbon dioxide or carbon that is coming from the mineral dust. Now, remember a situation during the measurements, if you do in this one, in principle what you are going to get? You are going to get EC, OC and CC also, okay, because unacidified samples will be giving CC. So, some of the time, some of the papers, if you see, they have erroneously used carbonate carbon as a fraction of carbon aerosols, but it is not the case, because carbonate carbon is not the fraction of the carbonate of the carbon, it is a fraction that is associated with the mineral dust. So, mineral dust concentration cannot be taken as a carbonate carbon. Okay. So, okay, so just let us come and complete this one. So, then you have a thermally dissolved organic material that will be actually evolved, they will come, and then you put actually like manganese dioxide oxidizing oven, there will be there. This manganese dioxide will convert all this into that carbon that came actually into the CO2 gases. So, once this CO2 gas is there, this again CO2 gas will be heated again, and in presence of nickel catalyst and hydrogen will be supplied. So, this CO2 plus H2O in presence of nickel and heating, this will be converted to CH4, and actually this CH4 is measured. So, effectively what you see here, for one carbon, you can see here that all the carbon that is there coming from here, they will be converted to CH4, and we are actually measuring CH4, and if your equation is stoichiometrically correct, then you can get that how much organic carbon concentration would have been there. So, this is measured as using the flame ionization detectors, maybe we will discuss. And then because your one product is actually methane, the good point is that actually this FID is measuring methane, and then you have to standardize your detectors, and this methane, after the end of the measurements, this methane is used as internal standard to see of a known concentration. Standard means of course it is actually a known concentration. So, known concentration methane is supplied, and this methane is measured by flame ionization detector. So, to check the detector's efficiency, and this detector efficiency is then used in the calculations. Okay. So, this is what was about the organic carbon. Then in the step 2, everything remains the same except starting temperature. In the organic carbon, you start from all the way from say room temperature, usually because you do not go whether the room for example, this time the room temperature might be 20 degrees centigrade. So, you start at 20, in the summer temperature might be say 40-45. So, you start with the 40-45. There is some kind of problem that is associated with this one, because there are research that they talk about that, okay, if you do not store the samples properly, some of the organic carbon might be lost, and even when you are opening or putting the sample collection, then this may be lost. So, yeah, this is that is always there, that kind of things, but that is true for the online measurement as well, because that you are collecting the samples in the either in the low temperature or lower temperature, or that temperature at room temperature say 25 degrees centigrade. So, and those artifacts will be there everywhere. So, in this one everything remains the same except the starting temperature, which is actually 550 degree centigrade, and then carrier gas. Here the carrier gas is actually helium plus oxygen. Generally we use 2% oxygen or 5% oxygen. This is volume by volume. Okay. So this is used for the, so this is actually then, and then the carbon dioxide that is there, the elemental carbon, because you are using now oxygen, then this elemental carbon plus CO2, this will be converted to carbon dioxide, and this carbon dioxide can be converted to CH4, and this CH4 will be measured by FID. So actually you do this way. Yeah, this is how it looks like. There is another method. Sometimes so there are two detectors, because then you can either convert this one and measure this as a FID methane. You can measure this as a FID, or the other way is actually this CO2 that is evolved, you can directly measure using NDIR, non-destructive IR, infrared spectroscopy. So this, for example, in the thermo-optical ECOC analyzer, the Sunset one, they have actually revised. Earlier they were using the FID, now they are actually using this NDIR detector. So you don't need to convert. So here actually what is happening, CO2 is not converted, so you don't need H2O plus CO2 in presence of nickel and heated one, you don't convert this one. So this process is not there, and here this detector is not FID versus NDIR. So I explained this one. Here it is what is happening. Here you have a carrier gas, whether it is helium or helium and oxygen, it comes here, and then it goes like you have a filter punch here, and then it goes through this one. You have a front oven which is heated, temperature are different temperature, we will come to that one, and then it goes that one. In you have a kind of a back oven here, where you have actually manganese dioxide oxidizer, which converts carbon into the CO2, and this CO2 can be measured directly as using NDIR or using as a kind of, So I think I will stop here, because okay, so this is very important. This is what the advantage is. So you use a laser here in this one, they used to use 678 nanometer, and what it do, it's continuously keep on measuring the transmittance through the samples. So at a point the sample, this laser beam will be coming, so this laser, because there are absorbing aerosols, so part of this one will be absorbed and then remaining will be transmitted. So we measure actually that how much transmitted radiation is there. So you have kind of intensity I, and then you have intensity that is transmitted, and then you can calculate that how much intensity of the radiation, laser radiation, is absorbed by this one, and you keep on measuring by a photo detector. So this becomes, and this is actually laser. This is used to see when the pyrolysis starts and when the split point is there. So I think I will stop. I will discuss this one in the next lecture, because this is, I still need 5-7 minutes on that one. So I will discuss this one in the next lecture. So I think you will get some idea on thermo-optical and optical methods. I will discuss optical methods separately, and in this methods, thermo-optical methods, I have just given a brief idea. So I think what will be good, if you can just revise these lectures, and then when we come to the next lecture, you already have some idea, and then so that it will be very easy for you to understand. So I will stop here, and we will meet you in the next lecture. So try to understand the concept, and we will introduce in the next lecture about this thermo-optical ECOC analyzer and ethylometer. Thank you so much. Bye.